Welcome to part 4 of the webinar series on securing IoT applications using Mbed TLS. My name is Handson, and I will guide you through this webinar about data transport layer security. In previous webinars, we have focused our attention on TLS, and DTLS was only briefly talked about. So why should we care about DTLS? If we want to secure TCP-based communication, such as HTTP or MQTT, TLS is a fine choice. However, many IoT deployments use UDP-based protocols such as the Constrained Application Protocol, COAP. Furthermore, DTLS can also be used for securing non-IP-based communication. Examples can be found in LoRaWAN, NB-IoT, or even with SMS. This webinar is structured as follows. First, I will explain the DTLS internals, then I will describe the testbed setup, and finally I will do the hands-on session. Let us first talk about the DTLS specification. DTLS 1.2 is specified in RFC 6347 and was published in January 2012. Version 1.3 is currently in development in the IETF TLS working group and will be discussed in a later webinar. The design of DTLS is intentionally similar to TLS. DTLS operates on top of unreliable datagram transport, and the two example use cases shown on the slide illustrate this. First, there is a non-IP-based transport example where COAP is protected by DTLS running over the 3GPP cellular IoT transport such as NB-IoT. The other example is a classical IP-based transport, where COAP is protected by DTLS running over UDP, over IP, and in this case over Ethernet. This protocol stack is similar to what we are using in our hands-on session. DTLS has become popular in the voice-over IP and real-time communication environment long before IoT developers have also recognized its usefulness. You may wonder why some designers, particularly in the IoT field, favor the use of datagram-oriented protocols such as UDP over connection-oriented protocols like TCP. In this slide, I would like to highlight the differences in terms of features. The assumption with most IoT applications is that they only transmit small amounts of data, such as sensor data readings from the IoT device to the server or commands to interact with an actuator. This ignores firmware updates. The transmission of this application data may not even require reliability. UDP lacks pretty much all features of a transport protocol except for port numbers and has become popular with IoT applications because of its lightweight nature. TCP offers a lot of functionality, as explained in a reference TCP for IoT guidance specification, and this comes at a cost, both in terms of code size and bytes on the wire. The two figures illustrate the differences in the header format between UDP and TCP. In addition to the larger header format, there's also overhead for the connection establishment and teardown. We shouldn't, however, forget that TCP also offers a lot of features, namely reliable and in-order delivery of stream of bytes, congestion control, flow control, and fragmentation support. Many IoT use cases do not need those features, and if they are required, they can be implemented at the application layer. One such feature that is often required is fragmentation and then reassembly on the other side, which is something I would like to focus on a bit more. Internet paths can have widely varying characteristics, including transmission delays, available bandwidths, congestion levels, reordering probabilities, supported message sizes, or loss rates. Furthermore, the same internet path can have very different conditions over time. A UDP-based application needs to have awareness of the maximum transmission unit supported by the path, the so-called path MTU. The transmission of payloads larger than the path MTU size will lead to fragmentation at lower layers, and most likely to inefficient delivery or to failure in communication. At the IP layer, the loss of a single fragment requires the higher level protocol to retransmit all the data in the original datagram, even if most of the fragments were received correctly. This fundamental issue exists for both IPv4 and IPv6. Additionally, mailboxes may drop IP fragments. Applications that transmit data over IP-based networks can assume an MTU of 576 bytes for IPv4 and 1280 bytes for IPv6, but they should transmit data smaller than these values to accommodate for the extra header space. To determine an appropriate payload size, applications must subtract the size of the IP header, which includes any IPv4 optional headers or IPv6 extension headers, as well as the length of the UDP header, from the BAF MTU size. DTLS also adds a header in form of the DTLS record layer. The size of it depends on the negotiated cipher suite. DTLS may also protect application data over non-IP based networks such as NB-IoT, or may require an adaptation layer to use IP over some link layers such as IEEE 802.15.4, which uses a very small frame size. Unlike application data protected by the DTLS record layer, the DTLS Handshake protocol provides reliable in-order delivery as well as fragmentation and reassembly support. If the application has information about the BAF MTU, then it can configure this value via the Mbed TLS SSL setMTU API command. The overhead for DTLS headers and encryption can be determined by the getRecordExpansion API call. The maximum application data size of a DTLS connection can be queried using the API call getMaxOutRecordPayload. Even if there is no risk of fragmentation for application data, the DTLS Handshake may still encounter challenges, since certificates or the new session ticket messages may be larger than the BAF MTU size. The exact size of those DTLS Handshake messages does, however, depend on the certificate chain, the type of certificates being used, and also the content of the certificates themselves. On the other hand, if the BAF MTU allows it, then the DTLS stack can place multiple DTLS records into a single datagram. This leads to fewer IP packets that need to be exchanged and consequently to a reduction in bytes transmitted over the wire. It also reduces the likelihood of reordering effects. This feature has recently been implemented in Mbed TLS version 2.13, and the Wireshark trace below shows the result. As you can see from the highlighted screenshot, the client key exchange, change cipher spec, and the finished messages are combined. Additionally, two other features have been added in the Mbed TLS version 2.13 library release. First, support for fragmentation of outgoing Handshake messages. This allows the use of Mbed TLS across networks with datagram links with MTU sizes as low as 512 bytes, making it suitable for NB-IoT networks. And second, reordering Handshake packets that have been received out of order. This reduces the number of retransmissions necessary to complete the handshake, and therefore increasing handshake efficiency and reducing network load. Here's an illustration of the DTLS 1.2 stack. The application layer protocol uses the DTLS stack to set up communication security by configuring the Handshake protocol, which negotiates the appropriate security association for use by the record layer. The record layer is always used and encapsulates all the protocols, including the change cipher spec and the alert protocols, which are not shown in the diagram. The application sends and receives application data via the DTLS stack. The Handshake protocol does not directly interact with the underlying transport, but instead always uses the record layer, even if no security context has been established yet. Unfortunately, it's not possible to just take the payloads defined in the TLS specification and to put them into a UDP datagram. A few adjustments have to be made. Starting with the record layer, two fields had to be added, namely the epoch and the sequence number field. The two figures show the differences between the DTLS and the TLS record layer headers. Since datagrams may get reordered and protocols like UDP do not offer reordering capabilities, a sequence number had to be added. This allows decryption of individual records. Stream ciphers such as RC4 are not supported in DTLS. This is not a big loss, since stream ciphers have later been prohibited also in TLS with RFC 7465. The epoch field was added to signal key changes, for example during rekeying. The Handshake protocol, which uses the record layer underneath, is also enhanced. The Handshake is a lockstep procedure. Messages need to arrive in a certain order and cannot be skipped. Hence, an additional sequence number is needed also for the Handshake protocol. Note that there are now two sequence numbers in play, one at the record layer and one at the Handshake protocol. Both serve a different purpose. When the Handshake is done, there is of course only a single sequence number used on the wire, namely at the record layer. Furthermore, two extra fields, the fragmentation offset and the fragmentation length, were necessary to support fragmentation and reassembly of Handshake messages. As mentioned earlier, this allows dealing with Handshake messages, not application data, that are larger than the path MTU size. Handshake messages may get lost. To detect and react on lost messages, the DTLS Handshake has its own retransmission mechanism. When a response has not been received in time, the Handshake message is retransmitted. A retransmission mechanism needs timers, and those need to be configured. The figure on the right side illustrates this concept. It is worthwhile to mention that retransmission does not actually happen at the level of individual messages. Instead, DTLS transmits so-called flights. A flight consists of a series of messages that travel in one direction. They are viewed as monolithic for the purpose of timeout and retransmission. As a consequence, DTLS messages themselves serve as acknowledgement messages, which means that no extra acknowledgement messages need to be sent. There is also a disadvantage, namely that retransmission requires an entire flight in case of a message loss. The retransmission concept is also relevant for an application developer, since timer callbacks need to be registered with the Mbed TLS SSL set timer CP function in your application code. The timing.c file contains the reference implementations of two functions, namely Mbed TLS timing set delay and Mbed TLS timing get delay. We will discuss how to implement these functions in the hands-on part of this webinar. Imagine a DTLS Handshake message gets lost. How long should the timeout be until a retransmission happens? Of course, the IETF RFCs offer some recommendations. The retransmission timer for TCP, as defined in RFC 6298 as a reference, suggests a default value of 3 seconds. Let us start with RFC 6347. The recommendation for the 1 second timeout aims to improve latency for time-sensitive applications such as voice over IP and gaming applications. At the time DTLS 1.2 was developed, real-time communication over the internet including voice, video, gaming was a big topic. Later, when IoT use cases became more popular, it turned out that the 1 second timeout was far too short for some deployments such as mesh networks, SMS, or even low-power wide area networks. With such a low timeout value, the result is that the sender too quickly starts the retransmission, even though the previous message may still be in flight. Hence, in RFC 7925, the default timeout was set to 9 seconds. In all cases, an exponential backoff procedure is used, which means that the timeout is doubled with every transmission. The maximum value is 60 seconds. The most appropriate value for the retransmission timer requires insight into the deployment environment. Hence, there is room for optimization if you do not want to use the default values. Mbed TLS allows the timeout values to be configured using the Mbed TLS SSL conf Handshake timeout function. There is a difference in handling integrity check failures between DTLS and TLS. In TLS, a connection is terminated when a record is received that does not pass the integrity check. An off-pass adversary cannot easily inject records since that adversary needs to guess the correct TCP sequence number. Hence, there's no reason to worry about off-path adversaries in this case. An on-path adversary is more powerful and does not need to malform packets, since it could as well send a TCP reset to produce a connection failure. For DTLS, the situation is different. An off-path adversary can easily send a fake record, since it only needs to guess the source IP address and source port of the legitimate sender. Hence, the DTLS 1.2 specification recommends not to tear down the session when receiving a record with a failed integrity check value. It is possible to set a limit to the number of bad records received before the connection is torn down. There is a compile time directive, Mbed TLS SSL DTLS bad MAC limit, and the API Mbed TLS SSL conf DTLS bad MAC limit allows you to set a limit in your application. Hence, you need to enable this feature via the compile time directive and then use the API command to make use of it. The TCP handshake performs a return routability check with the SYN/ACK exchange. The server can then assume that there is indeed a client at the given IP address. In DTLS, this is not the case, since UDP does not use a connection setup, and the server would have to respond to a potentially crafted packet with a fake source IP address. This could lead to amplification attacks, since an attacker only needs to craft a packet with the source IP address of the target and then send it to the server. A server would have to respond with a relatively large payload, namely with a server hello certificate, server key exchange, and a server hello done. There is also a risk of DOS attacks against the server itself, since an attacker is able to force a legitimate server to perform cryptographic operations by flooding it with fake requests. For this purpose, the hello verify request message was added in DTLS. Of course, the use of the hello verify request, as the figure indicates, adds a round trip. The hello verify request contains a cookie that has to be returned in a new client hello message, in the second client hello message from the client to the server. The cookie encapsulates necessary information that allows the server to verify the connection attempt without keeping state at the time of the initial exchange. If you know that these DOS attacks are not a problem in your deployment, you can disable the use of the hello verify request via the compile time directive Mbed TLS SSL DTLS hello verify. Most of the modifications to DTLS we've spoken about concern the Handshake protocol. DTLS primarily adds data origin authentication, integrity, and confidentiality protection to the application data. It is therefore interesting to see that DTLS also offers an anti-replay protection feature for application data traffic as well. This feature is enabled with a compile time directive Mbed TLS SSL DTLS anti-replay and the runtime setting Mbed TLS SSL conf DTLS anti-replay. If your application already has mechanisms to detect duplicate packets, then this feature at the DTLS level is not needed. Let us look at the integration of DTLS into the application code. There are actually only a few changes needed. First, Mbed TLS net connect needs to be told that we are using UDP instead of TCP. This is done by using the Mbed TLS net proto UDP constant. Second, Mbed TLS SSL config defaults is loaded with the Mbed TLS SSL transport datagram instead of the stream version. Finally, depending on how your application protocol interaction looks like, you might need to take the different semantic of a UDP-based protocol into account. This may have an impact on your Mbed TLS SSL read and your Mbed TLS SSL write interaction. The changes to the config.h file are rather small. You will have to add the Mbed TLS SSL proto DTLS preprocessor directive to enable DTLS support. Let me spend a minute on the hardware and testbed setup since I've changed it slightly compared to previous webinars. For the Handson, I will reuse BSK-based authentication developed in the first webinar and the hardware-based random number generator from the third webinar as a starting point. Then we will add DTLS support to it. We are still using the Hfile evaluation board with our STM32F407 MCU. I've changed the code to use the Cortex microcontroller software interface standard SimSys RTOS API version 2 and the RTX5, since I want to make use of convenient API calls to functions like OS kernel getDict count and OS kernel getDict frequency. In my previous hands-on examples, I've used RTX version 4 and SimSys RTOS version 1. Switching to RTX5 is, of course, not necessary, but useful when you want to take advantage of more advanced features. The DTLS server is running on a virtual machine on the development laptop. The development board is connected to the laptop using an Ethernet switch, and we only use static IP addresses in our example, so there's no DHCP or no DNS being used. To start the DTLS server, use the command shown on the screen. I also have Wireshark running on the development laptop to show you some packet traces. Let us now switch over to the Hfile Microvision 5 IDE to do the hands-on. I have the Hfile Microvision 5 IDE open and the development board connected. So let us first talk about the configuration settings for this project. If you want to get this code working, you need to make a few adjustments. As mentioned, we use an Ethernet interface with a statically configured IP address. And that IP address can be configured via the configuration wizard of the netconfig eth0.h file, which is this one. As you can see, I have used here a private IP, and I also disabled the dynamic host configuration protocol, since I don't use it in my setup. The IP address of the server side, however, which is running in the virtual machine, is configured in the DTLS_bsk.c file, which is the main application code. You can see that code here. Both the server board and the server name, or in this case IP address, is configured in that way. Furthermore, I have enabled UDP in the runtime configuration settings. So let's have a quick look at this, the networking stack. So here I enabled UDP support, and as also mentioned, I enabled the SimSys RTOS v2 and the RTX5 support, which can be found here. To use RTX5, I also had to make some adjustments in the code that I used in the previous webinars. So let's have a quick look at this. I now run the main application as a thread, and I have to start, obviously, the RTX5 itself. Not a big change, but still. Next, let us look at the Mbed TLS _config.hfile, where we have to add the Mbed TLS SSL proto DTLS define statement, which you can see here. Note that we still have to keep the Mbed TLS SSL proto TLS 1-2 included, since we are reusing the code from 1.2. If you remove this line, then you will get a lot of compilation errors. I've also included some of the other discussed DTLS specific configuration settings, namely the BATMAC limit, the hello verify request message for DOS resistance, and anti-replay protection for application data traffic. The remaining configuration settings have been discussed in earlier webinars already. Now we switch to our application code, where we need to make several enhancements and changes. First, let's start with the timers. In the two functions on the screen, I implement the timer callbacks to be used with the Mbed TLS SSL setTimer callback. Example callbacks for Unix and Windows are provided in timing.c, which is shipped with the Mbed TLS library, namely Mbed TLS timing setDelay and Mbed TLS timing getDelay. The setDelay function has three parameters, namely a void pointer to pass a timer context or a timer structure, and two delay parameters, an intermediate delay and a final delay parameter. Both values are in milliseconds. The final delay is used to indicate when transmission should happen, and intermediate delay can be used for implementation internal usage. I do not use the intermediate delay, so I skip that in the timer structure. With the setDelay function, we tell the DTLS stack when, in milliseconds, the retransmission timer expires. For this purpose, I record the delay time in milliseconds in a data structure, but also store the current tick count. The SimSys RTOS2 function for getting the RTOS tick count is OS kernel get tick count. The getDelay function determines the elapsed milliseconds since the setDelay function was called. If the elapsed milliseconds are equal or larger than the previously set delay, then the function returns 2. To turn the ticks into milliseconds, I use the OS kernel getTickFrequency function, which gives me the number of kernel ticks per second. Using the SimSys functions, the portability of my code is improved. Next, we have to register those two functions with the Mbed TLS SSL setTimer callback. This is the function, and as you can see, I'm passing in the setDelay and getDelay function as callbacks, and I'm also passing in the timer structure. Next, we need to look at the changes needed to the other Mbed TLS API calls. And I will start with the Mbed TLS net connect. In the Mbed TLS net connect function, we need to indicate that we are using UDP instead of TCP. We also, which is quite important, need to make sure that the networking stack has enough time to start. And so we can either use, for example, the OS delay function to introduce an artificial delay, or we can wait till the IP address gets configured, the interface, and the interface is up. And that's what I've done here. I'm using the net ETH_notify function to learn about the state changes on the Ethernet link. An example implementation is included in this file as well. Next, we need to look at the Mbed TLS SSL config defaults. We configure the stack with the default parameters and provide an indication that we are using the datagram transport. Next, I'm using the Mbed TLS SSL setBio API call to register my own send and receive callback function. This is not strictly needed, but may help you to implement your own transmission functionality. Finally, we have to make a couple of configuration settings using the Mbed TLS SSL conf. Here I configure the Handshake timeout, the AntiReplay protection, as well as the bad MAC limit. Finally, I'm setting an MTU size of 1500 bytes. Now we are actually ready to compile and run the code. So I have now started Wireshark, and you see the capture that Wireshark produced, and it's a classical DTLS 1.2 exchange. Starts off with the IoT device sending the client hello. The server responds with the hello verify request and includes a cookie, and we can also have a look at it, how this cookie looks like. So here you see the cookie value. In the next message, the client then includes this cookie and returns it to the server. As a consequence, then the server continues, everything is fine, sends a server hello and server hello done. The client then provides the client key exchange, change cipher spec and encrypted handshake message, which is this finished message, and the application or the handshake continues until we exchange some protected application data in this and this message. Then the exchange concludes with the alert messages, close notify sent by both the client as well as the server, and this is something we had written into the application code. You may also notice here that these messages are combined into a single datagram, which is the optimization I mentioned earlier with a new version of Mbed, with the Mbed TLS library. DTLS is a popular security protocol used in IoT deployments. for example to secure the constrained application protocol CoAP. If you watched the previous webinars about TLS, you are largely familiar with it already. There are, however, a few differences as well. We talked about reliable delivery of handshake messages which require the retransmission timer, denial of service features, fragmentation support for handshake messages, and the optional replay protection for application data. For an application developer, there are only a few minor configuration enhancements needed. The most interesting aspect is the use of timers for retransmissions. I hope you liked this webinar, and if you have questions, please drop me an email.